Hello, today we are talking about nitrogen monoxide pollution and Zel'dovich. Today we are going to talk about the work of Mr. Yakov Borisovich Zel'dovich. Um, so he was a guy who worked a lot in combustion science. He took part of the Soviet atomic bomb program and he worked on cosmology and black holes. So what will matter is a set of equation of mechanism um, that we will consider. So these three equations are part of his work. So they both involve nitrogen nitrogen monoxide in them. So these are the main equations. And for our study, we'll consider a fourth one that is just the split of dioxygen into oxygen. So these are reaction of a mechanism, so they don't need to be stable. So obviously O alone is unstable. And we give their constant of reaction, so the speed in which they um, are moving depending on various principles. So the first problem is we have a reactor with the following elements: N, N2, NO, O, and O2. So, but we said earlier we wanted to do a combustion, but back you can't do a combustion with that because there is no fuel in them. So actually, this occurs for any fuel because you don't need any fuel to have this production to occur. So we will consider a reactor with any fuel, but we'll just not consider that it intervenes in the reaction. And we are at a fixed temperature of 2000 Kelvin. We have partial equilibrium for the split of O2 into O plus O. We will consider that there is 60% of N2, so it's relatively close to the percentage in air. So it means you add a little bit of fuel for a big amount of air. And we consider that there is a 3% of monoxide in at the start of our study. So at first we will also consider that we know the standard enthalpy and the standard entropy for O2 and O. They are data that you can't know exactly, but that you can simulate for various softwares of thermodynamics. So as we will say, we will solve. So the first thing we can notice is that N in both those reactions is unstable. So by an approximation that is very used in a mechanism, you say that the derivative of N over time is equal to 0. So we just say that the variation of N is nearly equal to 0 because the quantity is very small. So the variation of N is so it's produced by R1, so the first reaction, because it's in a product. It's minus R2 because it's consumed in the reaction 2 and it's consumed in reaction 3. So we use the definition of the K in order to split it. So by definition, the reaction of a mechanism must have K, so the constant, times the concentration of each product by multiplication. So we get this expression here. We simplify to have the expression of N. Here we do a little approximation that K2O2 is superior to K3OH. So OH is something that is really small, and oxygen dioxide is um, really part of air. So there is a lot of of dioxygen in the air. So this approximation is legit. So we get this result here. Um, then we notice that that we have equilibrium for 4, as we said in the hypothesis. So we have activity of O because it's a product. So activity of of O squared over AO. So the activity is the partial fraction over the standard pressure. So the standard pressure P0. So you can convert it into concentration. So um, the amount of a reactive in a certain volume. So you convert from activity into pressure into pressure. So you get the concentration of O squared divided by O2, and to have the dimensionless, the same dimension, so K is dimensionless, you need to have P0 over RT, because PV is equal to nRT on a very nice approximation. So this is very valid. So you take this part, you simplify, you get this, and you replace K by the expression, so minus delta RG, uh, minus delta RG0 is equal to ln RT ln of K, because of various thermodynamics properties. So you get this, and the over 2 comes because we take the square root. So this we know how to calculate it because we have a thermodynamic properties. Delta Rg is equal to delta Rh minus T delta R S. So this we can calculate, and this we know it from the previous thingy. So we have the concentration of O2, that is by definition the partial fraction of O2 over RT. So the partial pressure of O2 into the air is the regular pressure times the product, the molar product of O2. So we said earlier that it was 3%, so it's this, and we get this nice result that is equal to nearly 10 to the power minus 7 mole per centimeters to the power minus 3. So as I said earlier, we have thermodynamic properties, so we can split this into this expression. We solve using the previous equations. We get all of our properties, so all of our results, and now we'll calculate the difference in NO2 in NO. So NO is produced in 1, is produced in 2, and is produced in 3. So it's the sum of all the reaction. So it's equal to all of this. What we can notice is that OH and OHN is equal to a very small amount, because OH is very rare in the field and N is very rare, even though K3 is 10 to the power 12. Because of this low concentration, this term is nearly equal to 0, and these are the main dominant term. So in our course they simplified it as twice K1 N2O, and I I don't know why it works, but apparently it works, and I have no clue why. So if anyone has an idea why this works, I'll be glad to listen to it. So they just take this and say that it's equal to twice this. So they get 4 times 10 to the power minus 9 mole per meter minus 3 second minus 1. But if you do it properly, which I did because I wasn't sure that this was correct, so I did it properly, and we get 3.98 with the same order as previously said. So we get this result here. We know the speed in which nitrogen monoxide is produced. So we get so obviously it's in a vapor state. So it's what in France we call vapeur nitreuse. So the vapor that are dangerous for human. So these vapors are expelled into the air. So what I did is I checked for what's the minimum regulation of the maximum regulation that we care for nitrogen monoxide. So it was in France and USA 25 ppm. So it's equal to 0.0025% of NO into the air. So obviously earlier we had a where is it? It's here. We had a fraction of 3%. So we suppose that the 3% stay in the reactor, and that the 3% that are not that are produced are expelled into the air, which is coherent because usually you work with a continuous flow. So we will suppose that the 3% stay the same, because if the 3% gets higher, the combustion is weakened, so it acts less because of the reactions, and so it will have an equilibrium because there is production of NO, and when there is production of NO, it weakens the reaction, so it weakens the production of NO, and you get a pretty stable result. So we'll assume that the 3% are constant, and that everything that is supplement is added into the air. So what I do as an approximation is I suppose that I calculate the total mole of in the air, so the total concentration into the air, in order to have um, an approximation of this. So it's not very rigorous, because if you add quantity into the air, obviously it increases the total amount, but we'll suppose that the quantity of air is so big compared to the production of NO that it doesn't matter. We don't consider that the number of total of mole will increase. So when we divide by the total amount of concentration, we get 10 to the power minus 4 ppm per sec. So as we said, we get 25 ppm max, and here each second we produce 10 to the power minus 4. So you can consider that with wind and with an open window, if you don't um, power on your reactor for like 10 years in a row without any air, this is not dangerous reactor. So that's it for this study, because 10 to the power minus 4, obviously to get 25, you need to have lots of time that is elapsed. So that's all. Thank you for watching. If you have any questions, feel free to ask them in the comments. And if you have any answer for the approximation 2K1, so twice the first reaction, I'll be glad to listen to it. and bye.